Question 10 of your maths exam will be a continuation of the application of calculus. And in this specific question, we will look into optimization. The question reads as follows. The oil and gas industry is one of the largest and most economically important industries in the world. The operations include refining of oil and gas into usable fuels before transportation as petroleum products. During the mining processes, oil and gas are extracted and stored separately. Oil is stored in an inverted cone. The height of the oil pumped is x meters, so this is the height, and the radius is x minus 3 meters as shown below. So basically they show us the oil and gas industry where they do the extraction and mining of oil. And you can see here that after mining the oil from wherever it comes from, the source, it could be in a rock or whatever, they separate the oil and the gas. So the oil would be taken and stored in an inverted cone like that, and the gas will go elsewhere. They'll store it separately elsewhere. Now what happens is that the oil obviously will accumulate here, it will start filling up, and then it will get to this height here where we have a height of h. So the height from here to here is an h. And you would see that when the oil accumulates, for instance, when the oil is at this point, this will be the radius. When the oil is somewhere here, this will be the radius. So the more the oil is filling up here, you can see that the radius also increases, it changes. So when it gets to this point, we'll actually have the radius of x minus 3. So we can see a relationship where the height changes and the radius also changes in this cone. Now, they further say here that the volume of a cone is given to be that formula. I think you know this formula, or if you don't know it, then at least you are given in this question. Now, they say here, show that the volume of the oil pumped is given by this formula. Now, when you look at this formula, it's a very interesting formula because we see here that the volume of the oil, so we're looking at the volume of the oil, meaning the volume that we have at this height here of the oil and the radius there. We can see that that volume actually depends on x. It varies as x changes. As I was saying, that if the height changes, the radius will also change. So that means our volume will also change because the volume depends on the height and the radius if you look at that formula. So it means this thing is like, when you look at it, it's a function of x. The volume is a function of x. X being the independent variable and our height, or the volume, not the height, but the volume being the dependent variable. So as we put different values of x here, we'll get different values of the volume, which is the y-axis. Our y-axis, if you look at it as a function. Now, to do this, we're simply going to use this formula to come up with this formula, because this formula is the formula of the volume, really. So we are on question 10, and we are doing 10.1. And we want the volume as a function of x, and we are saying here that our volume would be 1 over 3 pi, and our radius here, our radius r is defined by x minus 3, and our height is defined by x. So pi r squared, so half, we're saying 1 over 3 pi r squared, so the r squared here would be x minus 3 squared times the height, which is h here. And from here, this question becomes very, very, very boring, because we can just simply solve this and we should get the formula that we're given there. So this would be 1 over 3 pi. Then I'm going to expand that in the bracket, the binomial in the bracket, and we all know that this is going to be x squared minus 6x plus a 9. And we're going to have here the x. Maybe I can write the x here because remember, this x multiplies the whole thing here, so I can write my pi and x there. So this x, I've just moved it, put it there, because they're just multiplying each other there. Now from here, I'm going to do a distributive property where I take this whole number, multiply it with each term in the brackets there. So that now we are going to have here 1 over 3 pi x cubed minus. So if you say 1 over 3 times the 6 there, it should give me a negative 2. So we're going to have a negative 2 pi x squared. And when we multiply the last number, the 1 over 3 and a 9, it should give me a 3. So we're going to have a plus 3 pi x. So our answer should look like 1 over 3 pi x cubed minus 2 pi x squared and 3 pi x. And that's exactly what we have there. So basically we have shown that. So you can say here, hence shown. And this question really is worth 2 marks. So 1 mark for your correct substitution in there in the formula, and 1 mark for the final answer. Very simple and straightforward. Doesn't really require a lot of things for us to do here. Now we're going to jump into question 2. That says to question 10.2, that says to us, determine the height at which the maximum volume of oil can be stored in the cone. So what are we looking for here? We're looking at the maximum height. In other words, we're looking for the value here of x, the value of x, because remember x changes. As I said, we can change this height by putting in oil in here. So we want to find the maximum height, the largest height, the biggest height that we can have here, meaning here that h is equal to x. As we put in the oil there, and then this will be the maximum height in which we can store the oil, that we can have of the oil in the container there. Now to do that, we are going to actually then use our differentiation rules by differentiating the equation that we have here. Remember, here we have the volume as a function of x. So I'm going to take the derivative of my volume, because remember, we are storing the oil in the container. It will be the volume of the oil will take the shape of the cone. So in other words, when it takes the shape of the cone, it will have the volume defined in the same way as the cone itself. So now here we are going to take the derivative of this number, of this equation that we have. If we take the 3 here, we are going to have 3 over 3, which is really just a pi, and we are going to subtract 1 on the 3 there. So that means we're going to have a x squared there. Now if I take the 2 here, I'm going to have a negative 4 pi, and then I'm going to subtract 1 here. Then my x will just be an x. Then here we have an invisible 1. Remember, we're going to multiply this with a 3, so that I have a 3 pi. Then here I'm having 1 minus 1, which is a 0, and we know that x to the power 0 is just a 1. Now this is our derivative. This represents the derivative at any point. For the maximum volume, we are going to say our derivative is equals to a 0, because the maximum volume will occur when the derivative is 0. Remember, this thing is more like a function. As I said, it's a cubic function, and its derivative is a parabola. And at the stationary points, that's where we get the maximum, the local maximum and local minimum. And we know that the local maximum and local minimum occur when the derivative is equal to 0. So this means I can then develop this equation so that now I have pi x squared minus 4 pi x is equals to plus a 3 is equals to a 0, because we're looking at it at the maximum. You know, I can just divide here by a pi just to remove that pi to make my life easy. So here I also have a pi. I forgot to write that pi there. So I'm cutting out the pi. And by doing so, we then have an equation that will be x squared minus 4x plus a 3 is equals to a 0. And again, we know how to factorize this. We have done this plenty of time. So this means I'm going to have a 1 and a 3, and both of them really are negative in this case. And therefore, this means that my x is going to be equals to 1, or the x is equals to the 3. Now, these are the possible values of x, the possible values of height. Remember, x is the height here. These are the two heights in which we will have the maximum oil. But we have to test which one between these two will give us the maximum oil. There's two ways in which we can test this. So basically, these are our heights. We just want to find which one is the maximum one. Now, there are two ways in which we can test this. The first way is to use the first derivative test. First derivative test. With the first derivative test, what I do really here is that I will sort of do a table method where I will say here I have my derivative and here I have my values of x, the height that we actually are looking for. This is the height. And we know that somewhere here we have a 1 and somewhere here we have a 3. And here on the 1, we actually have our derivative to be 0. And here on the 3, we have our derivative to be 0. Remember, this is the derivative here. So the derivative is a 0. We have done that here at the maximum and minimum turning points. But we want to see which one is the minimum and which one is the maximum turning point here. So we know that here we have a 0. So, you know, this line here represents a tangent to the curve. So the tangent will be parallel to the x-axis. In other words, it has a gradient of 0. And we know that the gradient is the derivative. So the derivative is 0 there at those points. That's what I'm trying to say in a nutshell. Now, what we're going to do is that we're going to take numbers that are less than 1. Any number that is less than 1. And put it on the formula of our derivative, the gradient. So we want to see what gradient we have on the curve, or what is the gradient of the tangent on this side of things. Now, when we do that, I'm going to come to this equation really. Either I can use this one or this one. Actually, I'm going to use this one here, where we are going to say we really have here a pi, and we are testing a number that is below 1. So a number that is below 1 here, I can take perhaps, let's say a 0 is the easiest, right? And in fact, when I take a 0, I can quickly see that I'm going to have a 3 pi. But let's do it just for practice purposes. So here I have a pi as well. We multiply this pi by 0 plus 3 pi. So my answer would be a positive number there. If you look at it, it's a 3 pi. So if our derivative is positive, it means our graph is increasing. Or you can say the tangent. If I draw a tangent here, we'll have a positive slope. It will be a tangent that has a positive slope. So here we're having a positive, here we're having a 0 slope. Now, this side of things here, we want to take a number that is between the 1 and the 3. And that number there, maybe it can be a 2. I think 2 is the easiest. And then I'm going to put a 2 here. And if I put a 2, I get a negative number. That means my curve has a negative derivative. And a negative derivative would mean that the graph is decreasing. Or you can say the tangent is negative. It means I'm going to draw a line that is going downhill like that. And it has a negative slope. You have to notice that if I focus on this side of things, I'll also put, let's say, a negative 2, a 2 as we did there in my formula on the calculator there, and I'll still get a slope that is sitting like this here. So the slope between this interval is negative. I need to get lines that are going down like that. Now we're going to focus on in this interval. Now we're going to take any number that is above a 3. The simplest one could be a 4. Remember, you can take any number really. And this gives me a positive. So this tells me that my graph has a positive slope, and a graph that has a positive slope, it must be an increasing graph. Or we can say the tangent will have a positive gradient. So here we have a positive gradient and negative gradient. Remember, here at 3, our derivative or our gradient is 0. The curve has a 0 gradient. Now let us interpret this. If you look at this shape, you can see that I'm actually having here a graph that goes like that. And that means this point here 1 and this point here 3 will represent my turning points. And we can see here that here we have a maximum turning point and here we have a minimum turning point. Because this graph, this side here, it is concave down. Remember we said the n here, you see it here, it's a negative graph, right? It has a negative shape. It is a sad graph, our derivative there. Now when you look at this one here, it is concave up. And we said the U here represents the shape of this graph, right? It's a happy graph. That's why we have minimum and maximum turning point, the local maximum and local minimum turning point. Now this means at the height of 1, remember this was a height. This is the height that we have in our cone when we do the application on them, or the interpretation of this in the application of real life situations, right? Because it is a graph, but we're using that model of the graph to solve a real life solution, a real life situation. Now this means at the height of 1 meters, if we were to have 1 meters in this cone here, that's where we'll have the maximum oil to be stored in the cone. So that means here, to answer our question, we will then say here that therefore h should be equals to x is equals to 1 meters for maximum height. Because the maximum height occurs when x is equals to 1, when the height is 1. Guys, I would love to share with you also another method in which you can use this. And I would say you need to know both these two methods, because there are questions where they force you to use the second derivative test. And there are questions where they forced you to use the first derivative test. I think you have seen this in the previous question when we were drawing graphs. They've given us first derivative and second derivative, and they wanted us to sketch a graph there. So you need to be comfortable with these methods. So let's practice the second method. The second method is called the second derivative test. So here it means we are going to take the second derivative of this function, as the test name says, and then we're going to test that second derivative. Write this equation down so that I can be able to do this correct derivative here. So I'm going to have here pi x squared minus 4 pi plus 3. So this is a pi x squared minus 4 pi x plus a 3 pi. Then we are taking here the second derivative. So this is going to be 2 pi minus 4 pi. Because, the 3 pi here is a number. So the derivative of a number or a constant is really a 0. Now with the second derivative test, what we do is that we test our values again, the values that we got here, the values of x there, which are given by 1 and 3. So I will say at a height of x is equals to 1. I'm going to take my second derivative and put the 1 there, and we're going to say this is pi minus, remember this is pi x here. So I did a mistake on my derivative. Let me fix that. So this is pi minus 1. So I'm going to have here 1 minus 4 pi. And when we solve this, we can see that here we're just going to have a 2 pi. So 2 pi minus pi, that should give me a negative 2 pi. And this is a negative number. Do you see that this is a negative number? And we know that when we get a negative number, it therefore means that we have a maximum turning point or a maximum local turning point. Therefore, this is a maximum. This means that, remember we said that when the second derivative is negative, we are going to have a sad graph. Negative means sad phase. Right? So now, when we have a sad phase, it means then this is a maximum turning point. That's why we're saying at x is equals to 1, we're having a maximum turning point or a local maximum turning point. The graph is concave down. Another way of saying this is to say it is concave down. The n here tells you the shape of that graph. Now, because we're looking for the maximum, really, I can stop here and answer the question to say h is equals to x is equals to 1 meters for the maximum height. So the maximum height will be 1 there. It's very important to write this statement because you're going to get a mark for that. But if you were to then look at x to be 3, when it is at 3, you will find that our second derivative will have a 3 there, and we're going to have 2 pi 3 minus 4 pi, and this will give me 6 pi minus 4 pi. And this would then mean that we're having here a 2 pi, and 2 pi is positive, is greater than 0. That means now here we have a minimum. And obviously, in the same way, if the second derivative is positive, we're going to have a happy graph. It's going to be a happy graph. This was a sad graph. It's going to be a happy graph. And a happy graph would mean that we are having a concave up. Again, the U here is the same shape as our graph. Then this is where we have a minimum, but this is not part of our answer. We would have already answered that by finding that maximum. I was just showing you this part of things just to show you also, if they were to say find the minimum height, this is where you would have done it. Now, this question will be marked out of 3. So your first mark really will come from finding the values of x and also taking the derivative here. If you use this method, we'll get a mark, not taking the derivative, but saying the derivative is equals to 0, because remember, maximum occurs at 0. Occurs when the derivative is equals to 0. And the final mark here really will come by when you answer the question. Alternatively, obviously, they'll mark you if you take the second derivative, So you'll get another mark if you run the second derivative test. It will depend what method you use there.